Okay, everybody, we're now on to the third video in this new playlist. The playlist, as you recall, is for equation drill down, taking the equations apart. Well, in this video, we're going to talk about the 5 Kalman filter equations, and we're going to take apart, in particular, the covariance, the Kalman gain, and the covariance update equations. So let's get started. The heart of the solution for the Kalman filter is the Kalman gain. Here's the expression for the Kalman gain. It's a little intimidating at first, but you'll see it consists of components that we're already familiar with. We have P on the left side with H transpose mapping it, so to speak, into the space of measurements. And then we have this expression in brackets, which is an inverse, so think of it as a denominator. And it has HPH transpose plus R. Now R is a new matrix we haven't talked about yet, so let's get to that. R is the measurement noise covariance matrix. We'll define it in more precise detail later, but for now it's just another covariance matrix that governs how the measurement noise VK in the measurement model, how it evolves statistically. So if you recall, the measurement model was Z equals HX plus V, and so R is the matrix, covariance matrix associated with V. So where did this equation number 1 for the Kalman gain, where did it actually come from? So here's the equation again, and first we're going to say that we're not going to formally derive the equation. We will do that later in further videos, not in this playlist, but in subsequent playlists we will get into more detail into the statistics underlying the Kalman filter and more in-depth understanding of what covariance matrices are. However, we are going to take apart this equation and try to make some sense of how it works and why it makes sense. So first consider that the expression on the right has the form AB inverse, okay, where A is pH and B is the HPH transpose plus R. This is analogous to a scalar fraction A over B, i.e. a ratio. Okay, so if we now ignore the H matrix, pretend it's just the identity matrix for now, okay, since it really only maps the state space related matrix P into the measurement space, doesn't really contribute anything statistically. Think of it as just a scaling or projection factor. And like I said, just think of it as being the identity matrix for now. Then you'll notice that the matrices P and R are positive definite. Strictly speaking, the covariance matrices only need to be positive semi-definite, but we'll ignore that for now. So we are essentially considering the ratio of P to P plus R, right? If we ignore H. But P here is the extrapolated P that incorporates the previous P from the previous time step and the new element of the process noise, Q. So it's a covariance matrix Q, and it's also positive definite. So effectively, we are looking at the ratio of P plus Q on the top, if you will, to P plus Q plus R. Okay? So R is really the key item here. All right? If R were small, indicating that we have a nearly perfect sensor, then K would be near unity, and we would then effectively ignore the prior state estimate and just trust the measurement, which makes sense given a perfect sensor. You ought to trust the measurement. However, at the other extreme, if R were very large, then K would actually be near 0 because we would have a large number, if you will, or a huge matrix in the denominator. So K would turn out to be 0 or near 0. And we would effectively ignore the measurement in favor of the previously predicted estimate. So, using that gain equation, which here it is again, the state update equation, which we've already seen, is just written as x hat plus at time step k is equal to the previous predicted state x hat minus plus the Kalman gain times the measurement residual. So here, of course, z is the measurement and h is the measurement matrix. That's how k is used. And you can see how this equation indicates what I was saying in the last slide. If k were close to unity, then the term on the right, the h times the x hat minus, would effectively cancel with the x hat minus up front, and all we would be left with would be the measurement. If you think of h as being unity, or like the identity matrix in this example, if we ignore it, in other words. Okay, but on the other hand, if k were 0, then the whole right term would go to 0, and we'd just be left with the predicted state, which is x hat minus. So likewise, the error covariance matrix P can be corrected or updated using the gain. And this is how it's done. We take the gain, multiply it on the right by h to put it into the measurement space, and then we subtract it from the identity matrix for that space. And that becomes a scaling factor for P, the previously extrapolated P that we just talked about. Say, this is not a good form to use in numerical work, however. It doesn't preserve the symmetric nature of P. So it's better to use a form that's called the Joseph form, and here it is here. The only difference here is that we pre and post multiply the P minus by the I minus KH term and its transpose, right? And then the measurement matrix R is also pre and post multiplied by K and K transpose. This really does preserve the symmetry of P a lot better. So for numerically stable work, this is the form you really want to use. Okay, let's take apart that covariance update equation. Okay, so again, we're going to ignore h here and just look at I minus k. Thus, I minus k indicates, in a sense, how far we are from having no sensors at all. Okay, if k is equal to the identity matrix, then that says we have a perfect sensor. But if k is equal to 0, it says we have no sensor at all. So if k equals 0, then there would be no reduction in uncertainty, because that means we have no sensors at all. On the other hand, if k were the identity, we would have perfect knowledge thanks to perfect sensors, and therefore P would be equal to 0. In other words, we'd have perfect knowledge, right? With no variance in our no uncertainty, we have perfect knowledge. So typically k is between 0 and the identity matrix, and thus the use of I minus k to update the covariance will have the effect of reducing the uncertainty of P. Later, we're going to see how this form for k and its use in the update equations is in fact mandated by the requirement that we make optimal use of phi, p, q, and r. All right, so we now have seen all 5 equations for Kalman filtering. Here's the first one, state extrapolation. We just apply phi to the previously updated state from time k minus 1. That gives us the predicted state estimate, x hat minus. And then we extrapolate the covariance as well. And so P minus k is just pre and post multiplied of P from the last update at time step k minus 1, just pre and post multiply by phi and phi transpose, and then add in the process noise, or the process noise covariance in this case. Then we compute the Kalman gain. Now that we have P minus, we can use R and H and P minus to compute the Kalman gain, as we were just considering. And then we can use that to update the state with the state update equation. And finally, we can update the covariance with its updated equation, or its Joseph form, as I mentioned. And then the whole thing starts over again. We go back, we change K, and we go back to the top and do state extrapolation, covariance extrapolation, Kalman gain, state update, covariance update. And that's how the Kalman cycle works. So there's some definitions for each of the matrices that are in these equations. That P plus K is technically formally defined as being the estimation error covariance. So X tilde plus is the updated estimation error. And so we take that vector and multiply it times its transpose, and then take statistical expectation of that matrix. And we'll talk much more about that later. As I mentioned, this is the estimation error. And then P, we just call P as the covariance matrix. And then Q is also defined as an expectation of W, the process noise, times its transpose. So it's, again, expectation of a vector times its transpose, which is a square positive definite or positive semi-definite and symmetric matrix. The RK matrix is also defined the same way. It's the measurement noise covariance matrix. So where are we? We've drilled down on the Kalman gain equation, seen that it's a function essentially of P, Q, and R. We've presented the 5 Kalman equations. And so in the next video, we're going to look at 3 simple example applications that gradually increase with complexity. So you can see how this is actually applied in the real world. And that will do it for this video. Thank you for watching. We'll see you in the next.